Hi there, my name is Anne and thank you so much for clicking on this video. Today we're going to be looking at the shortest path algorithm. Now this is the last topic for graph theory in Unit 3. Later on in the year we will revisit graph theory again, but we'll be looking at some more complex algorithms that apply to a wider variety of practical situations. Anyway, these videos take me quite a long time to make, so if you do find them helpful, please support the growth of this channel by giving the video a like, subscribing or sharing the video with a friend. With that said, let's get to it. Okay, so to begin the lesson, we are going to give credit where credit is due. Now, Dijkstra was a Dutch computer scientist who was very influential and made huge contributions to developing programming language. Earlier on in his career, he invented the shortest path algorithm. An algorithm is just a set of steps or instructions that you can use to systematically solve a problem. So in this case, he created an algorithm that could help you find the shortest distance between any two nodes or vertices in a graph. And the way that it works is by keeping track of your currently known shortest distance to each vertex as you progress along the graph. So for the purpose of this course, I have condensed the steps down to these 5 on the screen here. The first step is to locate the nodes or vertices that are adjacent to your starting node or vertex. The second step is to consider the path that will provide you with a minimum weight to get you from the starting vertex to each adjacent vertex. The third step is just to write down the shortest distance that it takes to get from the starting vertex to the vertex that you're at. The fourth step is to repeat steps 2 and 3 until you get to the final vertex. And finally, step 5 is to backtrack along the graph so that you can identify the specific path that gives you the shortest distance. Okay, so let's put those steps into action with this first example here, where I'm going to show you how to use the shortest path algorithm. Let's read the question. Use the shortest path algorithm to systematically find the shortest path from A to H. Okay, so step number 1 is to locate the starting vertex and the vertices that are adjacent to it. So in this case, the starting vertex is vertex A, and the vertices that are adjacent to it are B, E, D, and also C. Step number 2 is now to consider the edges that provide us with the shortest path to get from the starting vertex to each of these adjacent vertices. Now, before we start, I just want to say that it is very unlikely, although still possible, that you have to go past the vertex and backtrack to be able to find that minimum path. Okay, so out of all the adjacent vertices, I'm going to start with the simplest ones, which are B and C first. So for vertex B, there really is only one edge that leads into B, and that minimum is 10. So I'm going to write that inside that vertex there. Next, I'm going to look at the edge that gives me the minimum distance to get to vertex C. And in this case, like I said, it's a simple one. It's just this 5 here. So that's what I'm going to write down in that vertex. Next, I have the option of working with vertex D or vertex E. However, I can see that out of the 3 edges that lead into E, one of them come from D. So I should start with D first. And in that case, I've got this 7 here. It's definitely less than that 9. So I'm going to write 7 inside that vertex. Now, the whole point of writing the cumulative shortest distance at each vertex is so that we don't have to keep going right back to the starting vertex to find that minimum path. All I need to consider are the edges that need to be added on from each of the vertices that we've already written minimums for. Okay, so now for vertex E, I need to consider these 3 edges here. And from B, the minimum is 10 plus 8 is 18. I then have from A to E, that's 6. And from this minimum of 7 plus 3, that's 10. Out of those 3 options, I have 6 as the minimum that I'm going to write inside the vertex. Next, I'm going to look at vertex F. So I highly doubt that I'm going to have to start from C and go forward and have to backtrack. It's just this direct edge here, which means 5 plus 9 is 14. Next, I'm going to look at vertex G, which has 3 main options to consider. From this minimum of 6, I need to add 2, that's 8. From this minimum of 7, I need to add 5, that's 12. And from this minimum of 5, I need to add 10, that's 15. So out of these 3, 8 is definitely the minimum, and that's what I'm going to write there. Now, just to keep track of the edges that I've been using for these minimums, for that 8, I used that 2. For that 6, I used that one there. So I'm just going to keep track of that as I'm going along. Now, for vertex H, I've got these 3 options that lead into H. 6 plus 12 is 18. 8 plus 6 is 14. And 14 plus 11 is 25. So out of those 3 options, my minimum is 14, and this is the edge that I used. So step number 5 is backtracking along the graph. Now, because I highlighted some of the edges that I used to get the minimum path to each vertex, backtracking is going to be a lot easier. So this path of 14 used this 6, this 2, and this 6, and that is my shortest path. A, E, G, and H, which gives me a total of 14 units. Okay, so moving on to example 2 now, which is an application of the shortest path algorithm. Let's read the question. Maribel has just started university and needs help to navigate the campus. The graph below shows the distances in meters between various locations at the university. Okay, so I've got a graph with vertices labeled A through to J, and these vertices represent locations like the car park, the library, and various faculty buildings. We can then see the paths and the distances in meters in between all of these. Part A asks us to use a systematic approach to help Maribel find the shortest path from the car park, A, to the engineering building, J. Okay, so with the graph back on the screen here, I need to find the shortest path to get from the car park, A, to the engineering building, J. The first step is to consider the vertices that are adjacent to my starting vertex. In this case, that's vertex B, vertex E, and vertex C. So starting with B, my minimum, quite an obvious one and a nice easy one to start, is a minimum of 800. Vertex C is another easy one, that's 500. Now vertex E is a little bit more complicated. I've got 3 main edges that lead into it. One of those comes from D, so I need to find the minimum to get to D first. That is going to be quite simple. I just need to add 500 and 530 together to get 1030. So now for vertex E, I know I'm not going to need to consider this path here because 550 plus 200 is more than 650. So 800 plus 650 is 1450. Then I have my 1600, and 1030 plus 490 is 1520. So out of these 3 options, 1450 is the lowest, and I used this edge there. Next, I need to consider the shortest path to get to vertex F. So I have two edges that lead into F. The first one, 800 plus 550, gives me a total of 1350. And my second option is 1450 plus 200, that's 1650. So the minimum there is 1350. Next, I'm going to look at vertex G. So I've got 1030 plus 1300. That's 2330. Next, I have 1450 plus 780. That's 2230. So my minimum there is 2230. Okay, next I'm going to look at vertex H and I. Now, because vertex I has three edges leading into them and one that comes from H, I'm going to start with H first. So I've got, looks like my only real option is 1450 plus 600. That's 2050. Well, may as well just write that straight into the vertex. Next, vertex I, I've got 1350 plus 1360. That's 2710. Then I have 1450 plus 1200. That's 2650. And then I have 2050 plus 540. That's 2590. So my minimum there is the 2590. Next, for the very last vertex, I've got 1, 2, 3 edges that lead into J. So 2590 plus 700. That's 3290. 2050 plus 1250, that's 3300. And 2230 plus 1020, that's 3250. So my minimum here is 3250. Now, my fifth step is to backtrack along the graph to find my shortest path. So my 3250 used this edge, and then 2230 used this edge, 1450 used that edge, and then that 800 there. So for part A, my shortest path is A, B, E, G, J, which gives me a distance of 3,250 meters. And that's what I'm going to write down. Okay, so my shortest path is A, B, E, G, J, and that gave me a distance of 3,250 meters. Now let's move on to part B, which asks us, how does the shortest path change for Maribel if she now needs to pass through the library, F? Okay, so with the graph back on the screen here, you can see that I've erased almost everything except for the shortest distance that it takes to get to the library. Now that 1,350 uses this 550 and this 800 here. And now I'm going to proceed with my shortest path algorithm from the 1,350 to get to J. So from 1,350, I can add 200. So that becomes 1,550 here at the cafe. From the cafe, I can travel to the languages building by adding 780. That's 2,330. Now from the cafe to the economics building, I'm going to add 600 to 1,550. So that's 2,150. And then I have 3 options leading to I. 2,150 plus 540 is 2,690. 1,550 plus 1,200 is 2,750. And 1,350 plus 1,360 is 2,710. So my shortest distance to the medicine building is 2,690. I'm going to write the 2,150 in there and the 2,330 there. Now, to get to the final vertex J, which is the engineering building, I need to add 700 to 2,690. That's 3,390. 2,150 plus 1,250, that's 3,400. And then 2,330 plus 1,020, that's 3,350. So as I suspected, we still keep this edge and this edge from the original shortest path, but we now have to detour a little bit to go through the library. And that gives us a minimum of 3,350 meters. So let's write that down in our answer. Okay, so the shortest path only slightly changed by visiting F before E. So our shortest path is now A, B, F, E, G, and J, and that had a distance of 3,350 meters. So we better say that Maribel's path increases by 100 meters. And we've stated the new shortest path and the associated distance. Okay, let's move on to part C. If the path between the cafe, E, and the languages building, G, is temporarily closed for maintenance, what is the shortest path for Maribel to get from the car park, A, to the engineering building, J? Okay, so unfortunately, the path from E to G is now closed. I'm going to scribble that out to make sure that I don't accidentally use it. Now, I'm going to fill in the vertices prior to vertex E because those are going to be unchanged. I've got 800 here, 500 here, 1,030 and 1,450 and 1,350 here. Okay. I'm going to start with vertex G and I'm going to add 1,300 to 1,030. That is my only option this time. So that's going to be 2,330. Next, I'm going to look at vertex H from E. So 1,450 plus 600 is 2,050. Next, I'm going to look at vertex I, and I've got 3 different options here. So 1,350 plus 1,360, that's 2,710. Next, I've got 1,450 plus 1,200, that's 2,650. And finally, I've got 2,050 plus 540, that's 2,590. So my minimum to the medicine building is 2,590. And finally, to vertex J, I've got 2,590 plus 700, that's 3,290. Next, I've got 2,050 plus 1,250, that is 3,300. And then I've got 2,330 plus 1,020. That's 3,350. So my minimum distance is now 3,290, and let's backtrack to figure out the shortest path. So 3,290 came from this 700, 540, 600, 650, and 800. So that is my newest shortest path, and I'm going to write that down in my answer. So with a temporary closure of the path from the cafe to the languages building, Maribel's shortest path is now A, B, E, H, I, J, which is 3,290 meters. Let's go one step further for the completeness of this. And let's go one step further for the completeness of answering this question. Maribel's shortest path increases by 40 meters. And that, my friends, is all I have for you today for the shortest path algorithm. If you found the video helpful, please remember to give it a like, comment, or subscribe to the channel. In the next one, I'm going to be introducing you to the topic of sequences. So I'll see you in that one. Bye.